Hi grade 12s, welcome to Saturday Extra, and we're going to be having a long 1 hour 15 minutes lesson on physical sciences, and today we're going to talk momentum. And as usual, my name is Tinyiko Kosa. Now, we're going to talk, like I said, momentum, a very interesting section in physical sciences for grade 12s. Now, what is momentum? Now let's perhaps begin by looking at what are we looking at in this lesson. We will of course be telling you, or I'll be explaining to you what momentum is, and in this very same lesson we'll be talking about change in momentum, and of course this is something related to a concept called impulse. So we'll be getting deeper into these things here. What is the change in momentum and how it is related to impulse? The principle of conservation of momentum. Now, this is one other very important section in momentum that you need to know in order to be ready for the end of year exams. We will also be talking about types of collisions. There are two types of them. We'll be talking about elastic collisions and inelastic collisions. And lastly, we will be talking about LO3 in physical sciences, you know, learning outcome 3, that where we talk about the relationship between science and our daily lives. And here we'll be talking about safety measures in car manufacturing as related to the whole concept of momentum. Okay, now let's get the ball rolling. Momentum. What is momentum? Now, momentum is the product of mass and velocity, okay? And its symbol is small letter p. So we use small letter p for momentum. And from the definition here of momentum, where we are told it is the product of mass and velocity, we can then write down the mathematical definition of this. Because if we are told this is a product of mass and velocity, we need to ask ourselves, what is a product? So mathematically, a product is an answer you get when you multiply. Therefore, momentum, which is given by the small letter p, is equal to the product that we get when we multiply mass of an object with its velocity. The product of mass and velocity is momentum. Okay, so that is the mathematical definition, or the mathematical formula that we use to calculate for momentum, small letter p. Now, from here, from the mathematical definition, there's something that we can tell about the units of measurement. Here we are told the unit of measurement for momentum is the kilogram meters per second. Kilogram meters per second, where does it come about? Remember, we've got P as a symbol for momentum, and we're saying it's mass times velocity. If we were to substitute the units of mass and the unit of velocity and see what the unit of momentum is going to be, we are going to reach to that end where we get to know that kilogram meters per second is the unit for momentum. Let's just do that right away. What is the unit of measurement for mass? The SI unit of measurement for mass is kilograms, times SI unit for velocity is meters per second. All right? Therefore, if we were to look at the unit of measurement for momentum, we would see that it's going to be kilograms meters per second. Okay, and that is where it comes from. That's why we are able to know that to measure momentum, we use kilograms meters per second. Right. Now, we are saying that momentum is the product of mass and velocity, is the product of mass and velocity. Now, what happens if an object is not moving? Because a moving object will have velocity. Okay. Now, if an object is not moving, it means you have got zero velocity. Now, if you have got zero velocity, you would have zero momentum. Why? Because momentum is mass times velocity. And in this case, it will be mass times zero because the object is not moving, and then you have got zero momentum, 0 kilograms meters per second. In other words, what we are saying is that stationary object has no momentum. Stationary objects, objects that are not moving, do not have momentum. Right. Let's move on. Let's look at example 1. Example 1 talks about a truck with a mass of 24,000 kilograms. And this truck is moving to the right at 10 meters per second. Calculate the momentum of the truck. Now, there is something that we also need to note here, that momentum is a vector quantity. Okay, so momentum is a vector quantity. Now, what do we mean by a vector quantity? It is a physical quantity with both magnitude and direction. Hence, here we are also citing the direction in which the car is moving. Because at the end of it all, if we were to calculate for momentum, we need to account for the direction because momentum is a vector quantity. Right. So calculate the momentum of the truck. We know that P means momentum. So momentum will be equal to mass times velocity. Now you would see that I'm always writing P equals m times v. Why don't I go straight and just say P will be equal to 24,000 times 10? Because I want to always make sure that I don't lose marks. Remember that for writing a correct formula down, you are given a mark for that. So I don't want to lose those marks. Right. So this would be equal to, what is the mass of the truck? The mass of the truck is given up there. It is 24,000 times. What is the velocity of the truck? The velocity of the truck is 10 meters to the right. Okay? 10 is 10 meters per second to the right. Okay? So what do I have at the end? 24,000 times 10. 24,000 times 10 is going to be 240,000. And what is the unit this time? Unit of measurement for momentum, kilogram meters per second. So that is the momentum of the truck. Okay. Now, remember, we are saying that momentum is a vector quantity. What we have so far here is the size, is how big this momentum is. What is left for us to explain here is direction. Now, where is the direction? They are telling us that the truck is moving to the right. So that becomes your direction. So the momentum of the truck is 240,000 kilograms meters per second to the right. That is the direction. So this gives us the size, and that gives us the direction. So we have accounted for momentum being being a vector quantity, with being a quantity with both magnitude and direction. Okay. Now, question number 2, let's look at this one here. A tennis ball of 500 grams, right, is thrown towards a wall at 12 meters per second. What is the momentum of the tennis ball? Let's write down what is given to us here. M, the mass, is 500 grams. We are also given velocity is 12 meters per second. What we know is that momentum is mass times velocity. And this mass here given to us is in grams. But grams are not the SI units of mass. The SI unit of mass is kilograms. Therefore, we need to convert 500 grams to kilograms. What do? We multiply that by 10 to the power minus 3, or you divide that by 1,000. So this will be equal to 500 grams divided by 1,000, so that we can have this in kilograms. So this gives us 0.5 kilograms. So the mass of the tennis ball is half a kilogram. It is then that we can substitute into the formula the correct value for mass, which is 0.5 times the velocity is 12. And that is what is going to be the answer here. Now, 0.5 times 12. This is half times 12. And half of 12 is what? 6. And this is going to be 6 kilograms meters per second. So that is the momentum of the tennis ball. Right. So simply, this is the basic things that you need to know in momentum, being able to calculate simple calculations. And it is going to get a bit more complex as we move on, but it starts here. If you master this, then you'll understand every other section that we're going to deal with in terms of calculations in momentum. Let's come now to impulse. Okay? Now, impulse. What is impulse? Impulse is change in momentum. Okay? Change in momentum. Now, in science, if we talk change of a quantity, we make use of the Greek letter delta, which means change. So change in momentum will be symbolized by this delta P. Delta P would mean change in momentum. Now, I need to explain something here. If an object is changing its momentum, remember that momentum equals mass times velocity. So it means if it started with momentum 1, it will then have, when it changes its momentum, it might now have momentum 2, which will be mass, still be mass times velocity. But then the question is, what has effected the change from momentum 1 to momentum 2? Okay? Now, if you check carefully, if we are looking at the same object, say the truck we spoke about, the mass of that object will remain constant. Now, if there has been a change in momentum, it means that change would have been effected by this value here, the velocity. Okay? Now, it would mean that the velocity of the object has changed from some initial velocity to some final velocity. Okay? So what would have happened is that the momentum 1 would have been mass times initial velocity, and momentum 2 would have been mass times final velocity. Okay? Those are the two situations that are happening. It's the same object, so it is with the same mass, but its velocity is changing from some initial velocity to some final velocity. Okay? Now, if we talk change in momentum, it means that we'll be talking the difference in the final momentum P2 minus P1. P1, let me stick to the numbers, P1, initial momentum. Now, you can work it out here to say, all right, my initial momentum is that, and my final momentum is that. So P2 being final momentum would be M times V final, minus initial momentum is M times V initial. All right? And because M happens to be a common factor here, now I'm talking a lot of mathematics, I can factorize it out. So M comes out, okay? When M comes out, because it's a common factor, then I'll be left with V final minus V initial. So this gives me, if you like, change in momentum. So change in momentum is M into final velocity minus initial velocity. What creates a change in momentum of a moving object is usually its change in velocity, because the mass of the object usually remains constant, or it doesn't change unless that object has exploded and pieces of the object has been thrown all over the place. Then yes, we can say the mass has changed, but in very rare cases such thing would happen. Okay, now the second part that we need to talk about with regard to impulse is that impulse is also defined as the product of the force acting on an object and the period of time in which the force is acting. Now, impulse or change in momentum is also defined as the product of the force and what? And time. So it will be force times delta T, the product of that. Okay? And this is the impulse. This F delta T is the impulse. Now, if F delta T is the same as change in momentum, then it is the same as if we're looking at that one object, mass into V final minus V initial. That's what it means. Therefore, we would say that F delta T equals mass into V final minus V initial. I'm taking it step by step so that you don't get lost. We don't lose each other along the way here. So if I were to calculate for the force that is creating this change in momentum, okay, this F, I can get it by using mass of the object times the change in velocity V final minus V initial divided by change in time. Okay, now this gives me the force that is acting on that object for it to change its momentum from one particular value to another, from an initial value to a final value. Okay, so that is one very, very important equation or formula, but understand where it comes from. Understand all these things, the impulse being change in momentum, delta P, and the fact that mass is not necessarily the thing that is changing in usual cases. We're looking at the change in the velocity of the object. So that is mainly the things that you need to understand here. Let's move on. Now let's talk about the principle of conservation of momentum. Now, this, if you like, it's a rule, it's a law, all right? Okay? And what does this law say? The law says total momentum in a closed system, will remain constant, so it won't change in both magnitude and direction. But this happens only in a closed system. Perhaps we need to explain a little bit by what we mean by a closed system. A closed system would mean that there is no external force acting on it, okay? So no external force acts, no external force acts on this system. So if we cut out every other external force acting in a system of objects moving, the total momentum of that system, and that system could consist of 2, 3, or 4, or even many objects, okay? So it becomes a system because we've got 2 or more. And in that system of two or more objects, the total momentum will remain constant in both magnitude and direction as long as there are no external factors affecting that situation, no external forces. Okay? Now, so where do we apply this principle here? This principle is applied in collisions and explosions. Okay? So we can have, that's why I said here that this system here, we're talking about 2 or even more objects. So this will be object 1 with mass 1, object 2 with mass 2. There could be object 3 with mass 3, object 4 with mass 4. But then this is mainly where we talk about the principle of conservation of momentum. But you can apply it in 3 or even more objects there. So it's a system. Now, this principle would apply when objects, say object 1, so mass 1, moves towards object 2, mass 2, and they collide, okay? And something happens there. This principle will apply there. Or sometimes you have got 2 or 3 objects or more that are together, okay? And something happens, an explosion happens, and they separate. So you have M1 there, and you have M2 somewhere there. They have separated. So from this situation to that situation, this principle will apply. From this situation to the situation down here, that principle will apply. The principle of conservation of momentum. Okay, so these are the 2 situations or 2 scenarios where we can apply the principle of conservation of momentum. Situations in real life could include where we have cars, moving, bumping against each other. You have got people rowing in a boat, and maybe they decide to jump out of the boat into the water and swim. In that case, we will see that particular situation as an explosion. 2 objects or 3 or 4 or many more exploding, separating from each other. So a person moving out of the boat into the water could be seen as a situation that shows an explosion, objects separating from each other. So the principle will apply in those type of situations. Okay, now let's now begin to talk about collisions. Okay, now when objects collide or when they come into contact with each other, there are 2 things that might happen. One, they can collide and separate after collision. That's one situation. Or they can collide and stick together after that collision. So we've got two situations here. We've got two situations here. Now, let's try and unpack this. If I've got two objects, okay, I've got object 1. Say it's a trolley. So this is 1. I've got object 2, another trolley. Okay? Now, when they collide, they can collide here. So this is the situation before collision. When they collide, they can collide. So we have them colliding there. That's the moment they collided. Okay? So 1 and 2 together. This is the collision. Collision. And then at the end, we see them separating. Okay, this is 1, this is 2. And this situation here, when it could be that this one is moving in that direction, this one is stationary or moving in the same direction or against that direction, it doesn't matter. But the fact is that they are going to collide. When they collide, in this situation here, after that collision, they separate. And they can separate, finding that this one is now moving in that direction, this one could still be moving in that direction, or even stationary, whatever the case may be. Now, what happens here? This is a system. This whole thing, it's a system. And in this system here, what will be the total momentum? The total momentum will be the momentum of 1. So P total, if you like, will be momentum of 1 plus momentum of 2. Now, what is momentum of 1? Momentum of 1 is mass of 1, this mass here, object 1, object 2. Mass of 1 times velocity of 1 plus mass of 2 times velocity of 2. Now, this is total momentum, but we have got a situation where there is this occurrence here. This is before the collision happened, and that is after the collision has happened. Okay, so we've got a situation of before collision and after collision. So this is before collision, and that is after collision. So this is the situation that we have. This is the incident, if you like. This is what happened. Okay, now, definitely after this collision has happened, the velocities of these trolleys are not going to be the same. So we need to identify these velocities as well. So what we will do is to say, okay, the momentum, the total momentum before, which will be given for object 1, will be given by M1. Sorry, that will be M1. Okay, that will be M1. Mass of 1 would say times the initial velocity, okay, of object 1 plus mass of 2 times the initial velocity of object 2. So understand this notation here, okay, understand that. But then let's then come to the same system now. Remember, it's a system after. The total momentum again is equal to momentum of 1 plus momentum of 2. But then, what is momentum of 1? It's mass of 1 times, this time, the final velocity of 1. Okay, you can put it that way as well. Plus mass of 2 times the final velocity of 2. Okay, so final velocity of 2 in that way. Now this gives us total momentum after the collision. Right. Now the principle of conservation of momentum says the total momentum here is equal to total momentum there. So momentum in the first situation, this one, equals to total momentum in the second situation there. So what does it mean in terms of our formulas here? This would mean that for objects separating after collision, momentum before, which is m1, v initial 1 plus m2 v initial 2 should be equal to that m1 v final 1 plus m2 v final 2. Now this is what the principle is saying. Right. Now if we have the second situation, the second situation says here we've got a system in this way. We've got the system in this way. Objects stick together after collision. What happens is that you've got a system where you've got the trolleys. There is the first one. And you have your second trolley. Okay? They collide. Okay, so the two trolleys collide, and after collision, we see them still sticking together. They move together in a particular direction, moving together in that way. So this is the incident. Okay, so this is the incident. And this is before, and that is after. So after collision, they stick together. Now, what is going to happen here? Let's look at it. Remember, total momentum here, total momentum is equal to, this is 1, this is 2. This is 1, this is 2. This is 1, and this is 2. So total momentum at the beginning will be mass of 1 times the initial velocity of 1 plus mass of 2 times initial velocity of 2. So that gives us momentum, total momentum before. After collision, we've got this situation. Total momentum equals mass of 1 times the velocity final, okay, of 1. But let me not write the 1 there because I want to explain something. Mass of 2 times velocity final. Why am I not having subscripts of 1 and 2 for velocity final? Because say after collision, those two trolleys stick together and say they move in that direction. It's just an example. They are moving in that direction together. So they are moving in that direction together. So they have got the same final velocity. So final velocity is the same in that way. Now, this would mean that the final velocity we can actually, because it's a common factor there if you like, VF, VF. We can factorize that out as P final being V final, which is the same for both, into mass 1 plus mass 2. Now this would mean that for objects that stick together after collision, what the principle will be telling us is that mass of 1, this is before, V initial of 1 plus mass of 2 times V initial of 2 would be equal to V final times mass of 1 plus mass of 2, because the masses are not the same, but the final velocities are the same. Okay, so that becomes your second situation where objects, when they collide with each other, they stick together after collision. So that's how we can work it out, or that's how you should try and understand it. Okay, now we can have a situation where objects were together in the beginning. Okay, so say those are the two trolleys. They are together in the beginning. But something happened, an explosion. Okay, so an explosion happens. An explosion happens there. When the explosion happens, we find that at the end, you have the trolleys separating in that way. Okay? What we will have there is the reverse of this one. So you start with, they have the same velocity at the beginning, m1 plus m2 equals, they separate after. So, but then, pardon me, this part here is initial now. Okay, so V initial, they are sharing the same velocity at the beginning. V initial into m1 plus m2 will be equal to m1, okay, and V final 1 plus m2 V final 2, because they separate. Okay, they were together in the beginning and they separate afterwards. So this is a situation where we're talking explosions. Okay, so that is how we can understand the principle of conservation of momentum. And perhaps when we come to examples, you'll understand this much better. But let's just talk briefly and quickly about types of collisions. Okay. Now, with the types of collisions, we're looking at two of them. The first one, first type of collision, we call it elastic collision. And the second one, inelastic collision. Now, what is an elastic collision? An elastic collision is a collision where the kinetic energy of, or the kinetic energy of that system is conserved. So let me just say remains the same, where the total kinetic energy remains the same. Elastic collision is a collision where total, so let me also put that, where the total kinetic energy remains the same. So you don't lose kinetic energy. In an elastic collision, there is no loss of kinetic energy. So we say no loss of kinetic energy here. Okay, now do we still remember what kinetic energy is? EK is half mv squared. Do not forget that. Okay, now obviously the opposite will be the case here with inelastic collisions. Inelastic collision is a collision where kinetic energy is not conserved. Inelastic collision. Inelastic collision is a collision where total kinetic energy does not remain the same. Okay, why doesn't it remain the same? Because kinetic energy is lost. Okay, so total kinetic energy is lost. So during that collision, kinetic energy is lost. So that would mean if we calculate for the total kinetic energy of the system, okay, before collision, and then we calculate for the total kinetic energy of the system after collision, and find that after collision, the kinetic energy, the total kinetic energy is less compared to the initial one, we would say that that type of collision is inelastic. But if we calculate and find that the total kinetic energy at the beginning equals the total kinetic energy at the end or after collision, then we would say that that type of collision is elastic. All right. So that's it. Now let's look at some examples so that we can see if we can apply what we have learned in situations to solve problems. Let's look at this question here, example 2. A 4-kilogram object moving towards the north at 6 meters per second decreased. So it was moving towards the north at that velocity. It then decreased its velocity to 3 meters per second whilst moving in the same direction. Okay? And the question is, calculate the change in momentum of the object. So we have got the mass of the object. Can you still remember what it is? Please have your pens and books ready so that we work together. The mass is 4 kilograms. V initial, it was initially moving to the north at 6 meters per second. Then it decreased its velocity from 6 meters per second to a final velocity of 3 meters per second. So that is what is given to us there. And we are told to calculate for the change in momentum. Now, delta P equals M into V final minus V initial. Okay? Now, because the change in velocity happened in the same direction, we are told in the same direction, it means if we take to the north to be positive, because this is a vector quantity, then all these velocities are positive. So the mass is what? Is 4 kilograms into V final. V final is 3 meters per second. All right? Minus what? Minus 6 meters per second. That is V initial velocity. The initial velocity is 6 meters per second. So that's what we have. So at the end, we have got 4 times 3 minus 6. It's minus 3. Okay? And then 4 times minus 3 is minus 12. What are the units? Kilograms, meters per second. Now, what does this minus tell us about momentum here? It is telling us that momentum is acting in the opposite direction of motion. So we'll say that the change in momentum is 12 kilograms meters per second towards south. Now, or you could just say 12 kilograms meters per second south. Why south? Because to the north is positive. We took it to be positive, but when we worked it out here, it's giving us a negative sign there. And that negative sign simply talks to us about direction. So negative is opposite of positive. If positive is north, then negative will be south. Okay, then negative will be south. Okay, so that is how we can calculate for that change in momentum there. Now the question is, if it took the object 2 seconds to change its velocity, now we are given time here. If it took the object 2 seconds to change its velocity, what is the magnitude of the force that caused the change in the momentum? Now here we need to know that there is relationship between impulse and change in momentum. Impulse is change in momentum, so impulse equals m into v final minus v initial. Okay, so F times, what is the time given to us? Times 2 would be equal to 4 into that. But we also know we don't have to really calculate that value there. We know what that value is. We have calculated it and we found it to be 12. Okay, so F would be equal to 12 divided by 2, and that will be 6. And what is F? F is force, and it is measured in newtons. Okay, now another thing that we can quickly see here as we look at this problem here is that we are saying that this change in momentum, this impulse, is F delta t. Now, if impulse is F delta t, force is measured in newtons, time is measured in seconds. So the units of impulse is Newton second. That we should be aware of from that particular formula there for impulse as well. Right, so Newton second is the unit of impulse. Okay, right. Now let's move on and see if we can work out solutions to example 3. Well, example 3 is a nice one. Let's look at it. A 0.4 kilogram ball travels at 20 meters per second towards a bat, okay? And it is hit back at a velocity of 30 meters per second. Calculate the force exerted by the bat on the ball if the time of contact is 0.01 seconds. Now, remember that we're talking about quantities that are vectors here. So let's list them. Some of them are vectors and some are not. For example, the mass. Mass is not a vector quantity, it's a scalar quantity. It is given to us, the mass of the ball is 0.4 kilograms. But we have got velocities here. We are told this ball is traveling at 20 meters towards a bat. Okay, 20 meters per second towards a bat. So let's just say towards, let's take towards the bat to be positive. This is very important for you to do because we're talking vectors. So anything away from the bat will be negative. Okay, so towards the bat, it's moving at 20 meters per second. So that is the initial velocity. It's plus 20 meters per second because we have said towards the bat is positive. Now, V final, what is the V final of the ball? V final is 30 meters away from the bat because it is now hit back at that velocity. So if it is hit back at that velocity, that will be minus 30 meters per second. Okay, that will be our V final. And we are also told that the time of contact between the bat and the ball is 0.01 seconds. Now, well, we don't have to worry about minus and pluses here because time is a scalar quantity. It doesn't have direction. Okay, now let's try and answer the questions now. Calculate the force exerted by the bed. Now the force exerted by the bed will be equal to m v final minus v initial divided by delta t. Right, now what is m? M is 0.4 kilograms into what is v final? V final is minus 30 meters per second. What is v initial? V initial is plus 20, so it's minus plus 20, which will be minus 20 meters per second. You divide that by the time. What is this time? 0.01 seconds. Now, what will that be? That will be equal to, we can work that out using a calculator, but perhaps let's just simplify it. Minus 30 times, plus minus 20, it's minus 50, okay? Divided by 0.01, right? And that will be equal to, let's quickly use the calculator to work this out. Okay, so we have 0.4 times 50, which is minus, of course. Then we divide that by 0.01. And what is the answer? The answer is found to be, remember we have got a minus, so it's going to be minus 2,000 newtons. Okay, now why minus 2,000 newtons? Okay, remember that towards the bed is positive. So this force was hitting the ball away from the bed. So if this is the bed, it's a very bad bed I've drawn. The ball is going towards the bed. The bed then hits the ball, and the ball goes that way. So the force applied by the bed is in this direction. And we said towards the bed is positive. So if the force is hitting the bed or is exerted on the ball in that direction will be negative. So hence we find it to be negative. But the question here said, calculate the force exerted by the bed on the ball if the time is that. So we would say that the force is 2,000 newtons away from the bed. Okay, so that is the magnitude of the force that is being exerted on the ball by the bed. Okay, so that's how you would solve that particular problem. Okay, now let's move on to example 4. Now example 4 is based on the principle of conservation of momentum. And let's see how you will apply this principle in a situation that actually happens in real life situation. Let's see. We have here some information. In a railway shunting yard, a locomotive of mass 4,000 kilograms travels to the east at 1.5 meters per second and collides with a stationary goods wagon of mass 3,000 kilograms. The two separate after collision. You see now the two separate after collision. So that's one of the key words here. And the goods wagon moves to the east at 2.8 meters per second. Okay? Now let's write some of the given information here. We are told we've got two things here. We've got the locomotive. Okay, so let me try and draw this. So say this is the locomotive. Okay, and it is of mass 4,000 kilograms. It is traveling to the east. So let's say this is to the east. That is the east side. Okay, and it is moving at 1,5 meters per second to the east. And when it is moving like that, it collides with a stationary goods wagon of mass 3,000 kilograms. And this one, its velocity is 0 meters per second because it is stationary. Now, after collision, we are told that the wagon moves to the east. So wagon, this is the wagon. The wagon now, this is after. Let me draw this line. After collision, wagon (3,000 kilograms) moves now to the east. So it moves towards the east at 2,8 meters per second. All right? And the two separate after collision. So after collision, we see this 400 or 4,000 kilogram locomotive not moving together with that. So they separate after collision. But what we don't know the V of this after collision. We don't know how it has been moving. The question is calculate the magnitude and direction of the locomotive immediately after collision. So because they separate after collision, from the principle of conservation of momentum, the formula I'm going to use is this one. It's the one that says total momentum before equals total momentum after, and because they separated, mass of 1, velocity initial of 1, plus mass of 2, velocity initial of 2 would be equal to mass of 1, velocity final of 1, plus mass of 2, velocity final of 2. Okay, so that is what I would have there. And what is mass of 1? Mass of 1 is the mass of the locomotive. It's 4,000 times initial velocity of 1. Let's take to the east to be positive. So this will be times positive 1,5 plus mass of 2 is what? Is 3,000. Okay, that is the mass of the wagon, goods wagon. Times, what is the initial velocity of the goods wagon? It's 0. And all this should be equal to mass of 1, 400, times final velocity of 1, we don't know, final velocity of 1, plus mass of 2, which is 3,000, times velocity of 2, we are given, that's the velocity of the goods wagon, 2.8. But we are told it moves to the east. So because it moves to the east and we're taking east to be positive, it will be 2.8. We won't put any negative there. Right, so this works out to be, let's look at the left-hand side of the equation, which is this top part here. Okay, so that will be 4,000 times 1,5. And what is the answer? That is So that it will be 6,000. So 6,000 plus. Now 3,000 times 0 is going to be 0 equals this one. 4,000 times V final 1 will be 4,000 V final 1 plus then 3,000 times 2.8. Let's work that out quickly as well. It's going to be 3,000 times 2.8. And what's the answer? That works out to be 8,400. 8,400. Therefore, 4,000 V final would be equal to, we're taking now this to the other side. It was positive, it is going to be minus there. So it's going to be 6,000, if you like, minus 8,400. This would mean that V final will be equal to, what is 6,000 minus 8,400? It will be minus 2,400. So V final will be minus 2,400 divided by 4,000. Okay, and then if we use our mathematical skills there, that comes down to minus 24 divided by 40. Now, what is minus 24 divided by 40? So that's 24 divided by 40, and the answer is 0. It's minus 0.6. All right, minus 0.6. And what is this? This is velocity we're calculating for. This is velocity V final of 1. This is V final of 1. So V final of 1 is minus 0.6 meters per second. What does this minus mean here? What does it tell us? It tells us that V final 1, sorry about that, tells us that V final 1 will be equal to 0.6 meters per second. Okay, meters per second. If it is negative, remember we took to the east to be positive. So if it is negative, it means it is to the west. Okay, so we have answered this question here that says calculate the magnitude and direction of the locomotive immediately after the collision. So the magnitude is 0.6 meters per second, and then the direction is to the west. So we calculate the magnitude and direction of the locomotive, the velocity of the locomotive. Let me clear out this question here. So the velocity of the locomotive immediately after the collision. Okay, so that's how you would apply the principle of conservation of momentum to solve problems related to systems in momentum. Remember I said that it's a system because it consisted of two objects. It can consist of two or more as well, but it remains a system. But when we're looking at just one, we're not yet looking at a system. Okay, now let's come down here to the last question of the day. Name and state in words the law you used to answer number 1. What was the name of the law? The name of the law is, so let's answer this question in 2 parts. The name of the law is the principle of conservation of momentum. the principle of conservation of momentum. Now, it is very important to understand the instruction of the question. The question says name and state. What we have done here in A is to name it principle of conservation of momentum. The second part of the question is we need to state it in words. How do we state it? The magnitude, or maybe to be precise, let me just state it in this way. Right. Total momentum in a closed system. In a closed system remains constant in magnitude, in both magnitude and direction. So it remains constant in both magnitude and direction. In both magnitude and direction. Right. And right, in concluding this lesson, allow me to talk about safety. Safety in the manufacturing of vehicles. Okay. Now, manufacturing of vehicles. And this is safety when we're looking at momentum as a concept in physical sciences. And specifically, we will be looking at impulse. Okay? Now, what is impulse? F delta t equals change in momentum. Okay? V final minus V initial, okay, in that way. So that is what we're looking at. Now, this force here is the impact that people inside a car would feel when a car is involved in an accident or in a collision. Now, this force here, you would see from this equation that its magnitude is determined by the final velocity minus the initial velocity times the mass divided by the change in time. Now, in modern cars, what happens is that they use this understanding such that if we make the time of contact, which is this time here, time of contact, if we make it longer, it means we are dividing this whole thing by a bigger number. And if you're dividing by a bigger number in a fraction, you're making that fraction smaller. So if this time is made bigger, so you are saying you are actually making the force to be smaller. Okay? And how do they do that? These cars are manufactured in such a way that they've got what we call the crumple zone. Okay? So if this represents a modern car, I've made my modern car very ugly, but it's modern. Okay? Now look at it. This part here, if this is the front part, it is made to have a crumple zone. So maybe the crumple zone is the whole of that part here, the CZ, the crumple zone, such that when it hits something, the crumpling should take time to move from there to that point there, so that the force which gives the impact is less. And in that case, people on board feel the less impact. So it makes injuries to be less, okay? Less injuries. And of course, reduces death. So it reduces fatalities in accidents. So that is one of the things that modern car manufacturing would do to ensure that people are safe. And they're applying exactly what we know in science, exactly what we calculate and talk about every day in our classes to achieve that particular safety issue when it comes to cars, right? And well, that brings us to the end of the lesson for today. I hope you enjoyed it. Till we meet again, and me, Tinyiko Kosa, signing out.